we are demystifying a fundamental data structure in computer science, the expression tree. If you are ever wondered how calculators, compilers, or even search engine person can evaluate complex expression efficiently, you are in the right place. I'm your guide and we will break down why trees are the perfect model for this task, how to build them, and how to make them work for you. First, we look at why use the expression trees and benefits. We can get three key points on this expression tree. There are clarity, optimization, efficiency. Let's start with the why. Why not just a processor issuing like this formula directly? Expression trees give us clarity. They turn an ambiguous sequence of characters into an explicit hierarchical structure. This eliminates any doubt about operator, precedence, or grouping. Evaluation becomes deterministic, just traverse the tree. This structure also makes optimization like floating, constants or rearranging terms much easier. Compare that to the linear string. It's a compact, yes, but it is a just text. To understand it, you need the full pressure every time. Making reliable change or optimization to a string is messy. The tree pays a small upfront cost in memory for massive gain in clarity and control later. Next, we can look at core component. An expression tree is built from just two types of nodes. There are operand nodes and operator nodes. First, operand nodes. They are the leaves. They hold the raw values like the number or variable name. They have no children. They are the endpoints. Second, operator nodes. They are the internal workhorses. They hold an operation like plus, minus or function call. A binary operator like plus will have the left and right child pointer pointing to the subtree that represent it is operands. Node data model. To implement this in code, each node needs specific field beyond just storing the value or operator symbol. We need left and right pointer to navigate the tree. Advanced implementation often store metadata like precedence, level or exclusivity within the nodes to make tree construction and optimization much faster. Let's talk about the structure and parent-child meaning. So, how does this structure represent an expression? Think of it like a puzzle. The parent-child relationship has a very specific meaning. A parent code is a combiner. It waits for the result from its child subtrees, apply its operation, and passes the result up. This order is critical for a non-communicative operation like subtraction or division. The left child is the first operand and the right child is the second. The subtree enforces the, which is why it is so unambiguous. Now you can see 6-step arrow diagram. How do we build this from standard infix expression? We use two steps, one for operators and one for operand nodes. This is the example for infix expression. The process of this 6-step arrow diagram. We tokenize the input, push operand to the I step and handle operators based on precedence. If we see a closing parenthesis, we pop and build nodes until we hit the matching opening parenthesis. Finally, we pop any remaining operators to from the root. Now I talking about postfix method and parser method. We build our tree from infix using a two-stack algorithm. Build there are other ways. A simple method is to start with postfix notation. You can convert infix to postfix using the shut-in-yard algorithm. Then built in the tree is the single stack push operands on an operator. Pop two nodes. Make them children of a new operator node. Push it back. It is very clean for expression. This is the example for postfix method. First, convert the infix expression to postfix method. Then, building the tree is the single stack. When you anything more complex, like a full programming language with function, commands and control flow, you use a proper parser like a recursive descent parser to build an abstract syntax tree. An AST is a more generalized expression tree. This is the method used in real compiler for its flexibility and robustness. Now you can see a parser method example. First, you can see expression, and next you can see what a parser does. Finally, show a AST representation. Now we can look how do we build this tree from the standard infix expression like this expression. The classic method uses two stack. We tokenize the input. When we see an operand, we create a node and push it onto the operand stack. When we see an operator, we check the operator stack. We pop any operators with higher and equal precedence. Build little tree with them and push those tree back onto the operand stack. Parentheses are special. Open parentheses get pushed, and when we see a close parenthesis, we pop and build until we find the matching open parenthesis. Now let's talk about our example. First we push 3 and we push plus mark and we push 5. We see multiplication mark which has higher precedence than plus mark. So it wait. We see open parenthesis. We push it. We build the 2 minus 4 subtree inside. When we close the parenthesis, we build the minus mark node. Then multiplication mark now gets popped. Combine 5 and the 2 minus 4 subtree. Finally, plus mark is popped. Combine 3 and the multiplication subtree. Give us our final tree root. Now you can see the final tree looks like. This is the visualize the final structure of the expression trees. The plus mark is at the very top. It called the root because it is the last operation to be performed. The leaf node 3, 5, 2 and 4 represent our raw data. This hierarchy ensures that 2 minus 4 is evaluate first, then multiply by 5 and finally add to 3. Now I talking about traversal mapping and compare result. One of the coolest thing about tree is the different ways of walking toward them called traversal. Give us the different expression notation. Three different traversal have expression trees. There are pre-order, in-order, and post-order. First, we are talking about pre-order traversal. Pre-order traversal start node, then left, then right. Give us the prefix notation like pre-order result example. It is used in languages. Next, in-order traversal. In-order traversal start left, then node, then right. Give us familiar infix notation like in-order result example. We add parentheses here for clarity as the tree itself has no parentheses. Finally, post-order traversal. Post-order traversal start left, then right, then node. Give us the postfix or reverse polish notation. Like post-order example. This is the perfect for stack-based evaluation as used in old HP calculators. It is beautiful. The same data structure can output all three forms. I talking about the expression tree uses. First, application. Compiler and interpreter are the big ones. Also calculators, symbolic math system, database query optimizers, and even templating engineers. Second, variations. The basic model extend. You can have unary nodes, function nodes with multiple children, or strongly typed nodes for languages like Java or JavaScript. Third one, pitfalls. Watch out for precedent and accessivity errors. When building your tree, don't forget to handle unary operators. They are easy to miss, and be careful when optimizing or modifying the tree that you don't break its structure. This is a video and I explain in this video definition and purpose of an expression trees, how operands and operators are represented as nodes, basic traversal to evaluate the expression. Thank you for watching my video. See you soon next new video.